big types of studies, right? I mean, there's more, but the other ones you just read through, they're pretty basic, pretty piece of cake. We got case control and cohort, okay? Gotta know them, slam dunk. Case control, A and an O. So they're doing a study, and right now in this study, someone has the disease and someone does not, okay? A and an O. Now, so they already have it, so do I really care what happens going forward? No, because we already know someone's got it, so no. So we're more interested in looking about what's happened in the past. That's called retrospective, okay? They'll use the word prospective, retrospective. In a case control, it's only about being retrospective. And when I say case control, you say odds ratio, right? One number to 1 over 1 number. And then the other one was relative risk. That's 1 number over 2. Stick with that and get them right each time. And the other study, we had case control, then we had cohort. Then we had cohort. 2 O's, right? Cohort, 2 O's. So right now, nobody has the disease. Nobody has the disease. So it could be retrospective or it could be prospective. We want to see what happens going backwards and then going forward. Now, they look the same. They are relatives, right? Relative risk. Boom. And that's it. And those are the 2 things you're going to, they just love those 2. And the other little things we can read through first aid are like, cross-sectional study. And those are just, you're going to read it and say, oh, that's what it is. But the main one is case control cohort, okay? What else we do? We did sensitivity, specificity, right? What do? We go to the chart. We easily draw it. What goes on top? Reality. Goes in here. Test or exposure, or whatever you call it. I just like to use test. It just works. Positive, negative, and positive, negative. Okay. Test positive. That's positive. True. Positive. Negative and a negative. True. Negative. Everything's based on the test. Test was negative, but in reality they had the disease. It's a false negative. Positive and negative. It was a false positive. And then we come up and we say, oh, sensitivity, what's my formula? I don't like to memorize it, so we say, oh, sensitivity goes down. Positive, true, positive, plus false negative, right? That's sensitivity. Specificity did what? Goes up. So specificity. That was a true negative over true negative plus false positive. Okay? Positive predictive value goes to the right. Positive over true positive plus false positive. And then the last one was negative predictive value. Goes to the left, okay? True negative over true negative plus false negative. Formulas are very fast, very simple. They're going to ask you one of those 4 things, guaranteed. And then we also had that question where we could turn it into words, right? They gave us a chart, they gave it in words and said this one's, it's 70% this one and 90% of that one. Okay, it doesn't matter. You go back to this and you can work your way through it. The other thing we talked about yesterday was when we move cutoff points. When they say they have a new test coming out, or they have the test and they want to move to the right or to the left, or they even move it down or up. It's all about, and all we care about is that center, right? Off to the left was true. False, negative.
True negative.
True negative. Good. Right? Over here, true positive. And we don't care about those guys. They never change. We've got to label it correctly, right? And then everybody keeps their last name. Okay? So there's our false negative, and then there's our false positives. So at the end of the day, all I care about now is, does these 3 lines, are they going to move the number down? Are they going to move it up? Or they can move it, as they did yesterday, they moved it down like that. Smash it, they both went down. So then we take that information and we just plug it back into these and we know the answer to any one of them. Okay? That's what we did yesterday. That's how it works. Very simple. Once you just go with that concept, all I care about is the center. But the key, where you mess up, where people mess up, you got to be able to label them correctly. Okay? You got to be able to label them correctly. All right, very good. So let me kind of work my way down to where we're going to start today. And bust through this. That one too. Sorry about the silence. I know it's never like silence. You lose people very quickly. Yeah. All right. Let's do All right, before we go into some other concepts, you're going to get this stuff. Here's just a question, and you know, again, I got these from. These are good questions. All right, so the table shows distribution of spot according to the death. Says what is the case fatality? Just take this home. I came across this over and over and over. When it says case fatality, they give you a lot of charts and graphs on this test, and they're not really interested in you becoming a biostatistician or whatever you want to call it. They just want to know, can you interpret numbers? You know, that's the basic concept. Can you interpret numbers? So, but when they say case fatality, if it says case, you stay within that concept. Don't get distracted by everything. They just want to know what is the case fatality rate for falls. Fatality meaning dying, right? So you stay within that. You don't worry about all this other garbage. Case fatality rate for falls. So here's my falls. How many people had falls? 20. How many people died of those 20? 4. Case fatality. When you hear the word case, just stay within the concept, okay? So, what's the case fatality rate for falls? Here's your choice? D. D. Simple as that. Just your take-home point for this question is that when you see the words case fatality, stay within the concept. I came up with this type of question over and over and over, and all I did was they changed what's the case fatality rate for, you know, occupational injuries, you know, and it was 6 out of 11, 6 over 11. Don't get lost in all this 4 out of 69, 20 out of 154. Again, it's distractors. Case fatality, stay within whatever topic we're talking about only. Are we okay?
Yeah.
All right, good. Again, over and over and over that came up. All right. We talked about, all right, here's the one. Good. Accuracy and precision. Okay, they like that one. I always had trouble with that, you know. But it's basically accuracy and precision. With accuracy, they got to give you some type of what am I shooting for? Where's my bullseye? You know, what's my normal? You know, and so we're aiming for that. If I get close to that, I'm accurate. Precision just means, man, you're really, you know, God, you did the same thing over and over and over again, but maybe it's kind of away from where it should be. You know. So again, accuracy, imagine it to the gold standard, the bullseye, or whatever mark, you know, the cutoff for diabetes. You know, if this thing, a new test wants to measure diabetes, but it has to have the new test has to have some type of baseline. And so, oh, we're going to make sure the control can get me to 120, you know, 120. So if that test comes up and hits 120, 122, you know, wow, it's pretty precise because it's right in the same zone and it's right where it needs to be. It's accurate, you know. But as you can see, you can be precise. This guy's real precise, you know. He was hitting all over right in that same little spot, but he wasn't where he needed to be. So was he accurate? No, but he was real precise. Hey, man, good job on that, but you're just off target. All right. So you have to know the difference between accuracy and precision. Okay, accuracy and precision. Accuracy, you got to have something to some type of gold standard, some type of baseline. I mean, you got to be shooting for something for accuracy to make it understand if you're there or not. Okay? Precision, you're just kind of off base. It's coming. All right? Now, they have all these biases. Now, you got them in your book. A lot of them are just one of those self-explanatory things. There's a couple of them that are your meat and potatoes. All right? And it's really this one called confounding. Step 1, step 2, step 3. They just beat this confounding to death, and I never really grasped it, really until now, you know. All right, so confounding. Basically, it's like this. They give you all these scenarios. They said, well, you know, they did a study and people with, you know, they smoke and they had some cancer, okay, but the study was really messed up somehow, you know. And then they go blah 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 blah, and you say, well, what was the problem? Chances are it was like a confounding problem. There was a confounding bias. Basically what that means is, say they smoked, and say there's a relation to cancer, but there was this other thing out there called alcohol, okay? And we could say alcohol, is it related to people who smoke? And you could say, well, there's probably a correlation. If you drink, you probably smoke. And then you say, well, is there a relationship between alcohol use and cancer? You know, if you drink a lot, chances are you're going to develop, maybe you might have a higher incidence of developing cancer. So this alcohol was related to the exposure and the outcome. So it affected this whole study they had. That's called confounding. Okay? They like They want to make sure that you can understand that when you're reading, you're reading some new report out of some journal, that you can at least interpret something. Yeah, there's some confounding problems, or you're creating a study. You got to take into consideration there's other factors out there that if you don't account for them, they can really affect your results. Confounding. The key is that it affects the exposure, and it's related to the exposure, and it's related to the outcome. It's related to both. It's a confounder. Okay. Now there's a scenario out there like shoe size. You're going to come across this question at some point. Shoe size and IQ. They say there's a study done in elementary school, okay, between shoe size and IQ. You say, well, yeah, look at that, man, look at that chart. Yeah, there must be a correlation. If you look at the bigger shoe, they're much smarter. Well, wait a second. There's probably a confounder problem in here, right? Because if you're in elementary school, chances are, if you've got a bigger shoe, you're in a higher grade. You've been exposed to more information. So that's a confounder that you need to account into your study. You just can't come out and say, hey, yeah, man, bigger shoe size, smarter the person. All right? Because is age related to shoe size? Yes. You get older as you're in elementary school, your shoe's going to get bigger. All right? And as your age, you need more exposure, you are going to be probably a little bit more smarter based on exposure. So age, in that concept, is a confounder related to both the exposure and the outcome. Okay? And that's it. But you got to understand confounding. Everything else, you can read through it. I won't bore you, I don't like people to read to me. All right. And then how do they control it? They say, well, what would you do with that? And really your answer is, I'd do better matching. When I did that study with the shoe sizing guys, I'd probably, let's put a little older kids in this, let's make sure we got some 5th graders over here, and some 5th graders, 4th graders, and 4th graders. Let's spread these guys apart. I'm going to do a better job on the front end with matching, and that'll control my confounding. Okay? That's what they're looking for. That's your question. Okay? It comes in words, but it falls under the biostats area. All right, we talked about this through here. Odds ratio, again, one number over one number. Relative risk, blah, 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 one number over two. They're going to give you the numbers. They just want to make sure that you can identify. And they might not say, relative risk. They might just come out and say a cohort study was performed, blah, 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 blah. And then you have to know, you got to make you got to use the relative risk formula. You got to make the association between those names. Odds ratio, case control, relative risk cohort. I know I sound like a broken record, but it's only because it's important. I promise you. All right? Now, the other formulas I said last time, I said, there were a couple formulas that I wrote down. Right when you get in there, you get 2 blank laminated things, and they give you a marker, And so that was one of the things I did. I was like, all right, number needed to treat was 1 over the attributable risk reduction or whatever. These are the ones I walked in there with, just because I wasn't really strong in them. And there's one at the bottom I'll go over, but there's only 3 of them. And for right now, just kind of look at you'll look at them, you'll play with them, and then eventually you'll write them down. You'll know I'm just going to write that down when I get in there. They're going to give me one of these, which is just basically a subtraction thing between reduction in risk between treatment and placebo. They're going to give it to you. And they're flat out going to give you those numbers. You're going to subtract them, and then you put 1 over that, and there's your answer. I know that's weak, and it's not a very good teaching moment for me here, but just remember, you're just going to write these down. You're just going to have a basic understanding. Attributable risk is just the subtraction of the control versus the treatment and reduction of risk, and you'll go from there. It's about as simple as that's as hard as it gets. If you go any deeper, you're going to get lost. Okay. Now, prevalence and incidence, very important. This was I came across this and I got it wrong. Okay, and it hurt. It stings later when you remember X number of questions when you come out, and I was like, oh God, what was this one? And I got it wrong. So you will not. All right. Prevalence is saying how many people have the disease, how many people have it, and how many people we got in here. So the prevalence of people wearing blue in here, I'd be like, well, how many people wearing blue, and how many people do I got in the room? That's the prevalence of blue. Okay. Now, incidence, and here's where this is the key. This is the key that I missed. Incidence is the number of new cases of a disease, disease in the population, divided by the total population at risk big disclaimer right here, we cannot include people with the disease when we make that number. Okay, you're going to get all this data, and they're going to say what's the incidence of the disease, and bottom line is, they're going to give you the number of new people that happened in 2010, but you got to subtract the people that the total population minus the people who already had the disease. They get out of the denominator, okay? We'll come across a question like that, but that's your take-home point. Incidence, number of new cases. There were 100 people in 2010 that developed some disease over the total population at risk. Well, in 2010, we got to take the population minus the people who already had it, okay? That's your, when they test it, they want to make sure that you understand that. They don't really probably care about prevalence so much. That's too easy, okay? They want to make sure that you can take this number and get rid of the people who already have it. I missed it. All right, so when prevalence is greater than incidence, in prevalence, that means the total number of people is so much more than the total number of new coming in. Well, that's like a chronic problem, right? It's almost like diabetes, right? That's it. There's so many people in America that have diabetes, and the number of new cases each year, yeah, it's happening, but that number is so much greater. That means it's a chronic disease. You can make that assumption. But when those two numbers are equal, that means it's an acute, right? Number of new cases pretty much equals number all that's out there. Well, okay, that makes sense. That means it's something new coming up. Something like, let's just say Ebola or something like that, Those numbers, prevalence and incidence, is probably going to be roughly the same. But something like diabetes, prevalence is going to be much greater because it's been around a lot longer. Okay? Very good. You're going to come up with this thing called this relative risk. They don't beat it to death in step 1 a lot, but it's fair game. And everything's fair game. And relative risk is just a number that kind of floats around 1. Okay? 1 means that it's like an odds. Well, that means that the chance of me having something is, if it's 1 to 1, then there's not much of an association. It's right up. But if it's greater than 1.5, or that means I have a 1.5 greater chance of something happening to me when my relative risk is greater. Okay, that's how I measure it. So when it's 1, there's no difference between the exposure and the outcome. If I use green marker, that that would do something better. Well, the relative risk is 1 on that. There's no association. Okay, but if I use Q-bank questions, or I use NBME questions, my relative risk, my relative to you guys of learning this stuff is going to be greater than 1. You got a 5 times, relative risk might be 5. You have a 5 times more likely chance of understanding something if I can run some old questions by you. Okay, so that's relative risk. When it's 1, there's no association, there's no difference between exposure and outcome. Doesn't matter if you were exposed to smoking or you weren't. The disease didn't happen or not. All right. Relatively good on that. Kind of blank scares, but a lot of times we just got to get to some questions. I don't know, we didn't get this one, did we? I don't think so. Nice. Here we go. Question: a new instrument is being purchased by the hospital that checks serum levels of X. Okay, whatever. The published value for the standard is 40. The technologist runs the test on patients and gets readings of 70, 68, 72, 75 respectively. What can be concluded about this instrument? Very important. Okay? We talked about 2 things. We talked about accuracy and precision. Okay? We said accuracy was what?
Bullseye.
Yeah, they got to be right. They got to be aiming for the bullseye, or my gold standard, or my set amount. That's accuracy. My precision is boom, 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 right in that little area. But maybe you were just off the mark a little bit. So if the gold standard's 40,
B.
yeah, B, right? Yeah. He was in the ballpark the whole time, but he wasn't very accurate because our gold standard was 40. Okay. If you know that concept, you're going to answer this question right. And that's the one they're going to beat around right there. That's the one, if I was making a test question, which I might, this is how I would kind of ask it, because I know you got to understand what precision is, and I know you got to understand what accuracy is. Okay? So there it is. Answer choice B. Very good. All right, so at the bottom of this one, this is just after that confounding. And again, confounding is related to what? Both the exposure and the outcome. Okay, both the exposure and the outcome. And there was one thing, I think it was called effect modulation. Yeah, it's called effect modulation. It comes up, not as much as confounding, but effect modulation says when something only affects one of the groups. He's an effect modulator. He's only related to one, not the other. Okay? Just know it. All right. And these other ones is just more of a definition thing. They like them, but you see them a lot of times, and it comes up. Lead time bias. It's a good one. It's a good one because they say, diseases and in this city have, more people are living and living longer in this city. What can you conclude from that study? Well, you can conclude a couple different things. You could say, well, maybe they're just detecting the disease earlier. People aren't really living longer. They're just getting diagnosed a lot earlier. They might be still dying at the same time. But it just looks like it's longer. So that's what's called a lead time bias. Whenever they start developing these new tests, which they do all the time, right? The science is getting better. This thing comes up called lead time bias. They're just detecting it. They're detecting the breast cancer earlier. So it makes it look like people are living longer, okay? When in reality, survival is roughly the same. All right. Of course, Pvalue, Hawthorne effect, burdens, it's all in there. It's boring stuff. All right, here we go. All right, now p-value. P-value, very important. P-value, just remember this. The sooner you get this, the better life becomes. P-value just says, what are the chances of this just happening by chance alone? Just total randomness. Okay? So p-value, you'll always see it, it'll always come up, but they like that 0.05, and that's just a mathematical number that all these mathematicians came up with that says if something has a p-value of 0.05 or less, that it means it's significant. Okay? So p-value, what's the definition of it? Basically, if something happened by chance alone. Okay, chance alone. So to make it, so if my study up here has a p-value of, 0.2, is it a good study? No. It's got to be a p-value of 0.05 or less. They love that. There's all these questions and they have all this blah, 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 blah. And then basically it says p-value of 0.1. And then basically you say, well, man, the study was invalid. It's not a good study. So you erase it. All right? Confidence intervals, it's almost like relative risk kind of thing. Just read through it. When you come across questions which you made, that's the best time to learn that. Otherwise, you just stare at me. All right? Now, these are some definitions. Meta-analysis, you get these things and you'll say, what type of study is this? And the moral of it is, meta-analysis, you're going to learn pulls from multiple sources. Boom. Enough. That's all you need to learn. T-test, comparison means between two groups. That's all you need to know. This is just flat out memorization. There's really no exciting way to do this. ANOVA, okay, comparison means of 3 or more. ANOVA, I got 3 syllables, I can buy that. Chi-square, anytime you see a 2x2 table and they say what type of test is this, just go with chi-square. Boom, do it, get it right. All right, likelihood ratios, again, you're always hovering around that 1. And so if it's greater than 1, results, it's more likely to happen. Okay, if it's less than 1, it's less likely to happen. Didn't see it so much on step 1 stuff that came up on a lot of my step 2 and step 3, but I've been in that situation where I'm sitting there on a Q bank or a test in step 1, and then where did this come from? This is like literally during the test. Like, who designed this? And it's stuff that I didn't learn later until I started studying for step 2 and step 2. So I just want to put it on there for you. So if you see it, you say, oh, okay. I still don't know what it is, but I do remember hearing talking about it. All right. So likelihood ratio, again, you're hovering around the 1. It's more likely to happen, less likely to happen. That's kind of the definition. All right. Very good. Standard deviation. The best type of study is a double-blind study, right? Nobody knows what's going on. It gets results. It's unbiased. All right. I'm saving this for last because that's that null hypothesis. That's kind of good stuff. Down here we have those little chart things, right? There's does something go this way, that way, and all you're going to do, basic math. You draw, you get dots, you draw a line, and you say, well, okay, well, it's a positive correlation, right? If something goes up, the more I study, the higher my grade. All right? So it's a positive association. The more I study, the higher my grade. So then I say, well, if I go over 1, up 1, that's like a +1, +1, right? It's positive. So, and then if these dots were more down here, not quite that, the slope, not here, right? Somehow like I know it, right? Slope means like if I went over 2, well, it's always the y-axis goes on top. So if I went up 1 over 2, it's like a 4.5, but it's still positive, right? If I do something, the more I study, the higher my grade. It's still a plus 1. So you have to understand 1, up 1 over 1, and this one's up 1 over 2, 1/2, 0.5. It's all positive. Right now, just know it's positive going that way. And then if I had it like this, well, that line looks like it's more that way. Well, the less, I'm not going to say study, the
less partying, the better.
The what now?
Less partying.
Very good. The less partying I do, the higher my grade. So the less studying, that's a negative concept, right? The less is down, the increase, and that's positive. So of course, a positive and negative make a negative correlation, all right? I always told the kids, I said, look, when you do all this math stuff, if a good thing happens to a bad person, that's bad. If a bad thing happens to a good person, that's bad. And if a good, all that kind of stuff. Or you can just flat out memorize it, whatever you like to do. All right? But you got to know, it's coming. All right? It's coming. Positive associations, negative association. And you got to understand, they're going to, there's questions out there where it's like, man, it looks like it's a 1. Where's it a 0.8? You don't know. So really understand what 1 looks like. It's exactly over 1 inch, or up 1 inch, over 1 inch. That would be a 1 going that way. All right? So that's this little box right there. All right? And then we have this thing called the standard deviations. Man, you got to memorize it. Hands down. Got a great question coming up. I love it. All right? Standard deviations. Standard deviation just means how far away am I from the mean? Here, it's right here. The standard deviation says how far away am I? If I'm right here, I'm 1 standard deviation. It's really on both sides of the mean. So 1 standard deviation. That just means that there's 68% of the people are probably in there. Okay? When I go out 2 standard deviations, 95% are in there. I'm getting farther away. Because if I'm outside that 2 standard deviations, I'm just one of the 5% of the people out there. It's not very, not very good, I guess. Depending on what it is. And if it's 3 standard deviations, 99.7. But you gotta know. You flat out have to understand that. The one they love is at the 2 standard deviations. Because it's 95%. Why? Because it starts talking statistical significance. So 1 standard deviation, 68. 2, 95. 3, 99.7. Gotta know. And there you can see this bell-shaped curve, or it's just a statistics, so they like these curves. Like, so 68%'s in here, 95%'s in there. And if I go out 3, 99.7. Man, if you're outside that, you're just you're out there. All right, very good. Now, the last concept before we get the rest of these questions is this null hypothesis. It's not that bad, okay? It's not that bad. Because we come up, we do this little 2x2 table, all right? We only got to draw this one at a time, with our true positives and all that stuff. Null hypothesis. Well, we're still going to come up here, and I like to put reality up here. But then I like to say, we'll put, I don't know why I put study on there. I'll probably realize it in a second, I guess, when we go through it. All right, then we have this study. Reality, and here's the study. Instead of test, I'm putting it's the same test, all right? So, the key to this is labeling it correctly again. And this again, I always had trouble memorizing this, but just remember the 1 goes first. So the H1, and then over here the H with the 0, and that just means the null right there, null. And null just means there's no association, okay? That's it. If you just memorize that, null says there's no association. H1, H0. All right? This is the whole null hypothesis. So there's no Null means no association. So, now we have to label this thing. Let's think about this. If the study said there's an association, but in reality there wasn't one, it's like it happened by chance. Because in reality, it just didn't happen. So that's called an alpha error. You got to know these in words. You got to put this box in the sentences. That's how you pass this portion of the test. You got to put this box in the words. The study said there was an association, but in reality there was not. They call that an alpha error. Alpha error. Boom. Right? The study said there was no association, but in reality there was one. They call that beta. Type 2. This is type 1. Okay?
The beta error.
Beta. Yeah, beta error. Again, put this in the sentences right here. This is how it likes to be tested right here. They like to know that you can understand that when they said, this test said there was no association, but in reality there was one, then they stick a value for that. Okay, I can buy that. So I know in words what that means. I can put a value here because this box right here is 1 minus beta. So I know if I'm creating a test what I'm going to do. I'm going to turn this into some type of sentence to know if you can give me some value. I don't care what it is. I'm making up a number. 30% or 0.3, same thing. So then I know what's 1 minus that. 70% or 0.7. Okay, I'm just throwing out a number. Anyway, that's irrelevant for the most part. But you got to know in words. So what's null mean? There is no association. Null. No. There's an O on there. No association. The 1, there is an association. So the study said there is, but there really wasn't. It's an alpha error. Type 1 happened by chance. Okay? It happened by chance. Usually this guy comes up like 0.05 just because that's significant. The study said there was no association, but in reality there was one. That's called a beta error type 2. That's your money.